Gravity, the thing that pins us to the Earth, makes apples fall from trees and keeps the moon dancing around our planet. Ask almost anyone and they'll tell you gravity is a force, a mysterious invisible tug that pulls objects towards one another. That's what we've been taught since childhood, Newton's apple and the idea of a force of attraction between masses. But here's the twist, that's wrong, or at least incomplete. According to Albert Einstein's general theory,
Curious about how the world really works? Not the myths, not the shortcuts, the real science behind everything we see and experience. On this channel, we explore mind-bending physics, unravel the secrets of the universe, and uncover the hidden patterns that shape our reality. If that excites you, subscribe for weekly deep dives into science and discovery. Hit like and share with friends. Your curiosity drives our next adventure. Leave a comment and let us know what puzzles we should solve together.
there are no invisible gravitational fields pulling us down. In fact, gravity itself might just be an illusion, an effect of something much deeper. And in this video, we're going to peel back the layers of what everyone gets wrong about gravity. So buckle in, because to really get it, we'll have to take a trip into space, climb rooftops with Einstein, bend light around the sun, and even ride an imaginary rocket ship through space-time. By the end, you might not think about standing on the ground or falling through the air the same way ever again. 3, 2, 1, liftoff. Einstein's happiest thought. Albert Einstein once said that the happiest thought of his life came not while publishing a groundbreaking paper, not while winning the Nobel Prize, but when he imagined something oddly simple. A man falling off the roof of a house. It sounds cruel. Why would that make him happy? But Einstein wasn't thinking about the poor man's fate at the end of the fall. He was thinking about what the man would feel during the fall itself. The answer is nothing. While falling, the man would feel weightless. He wouldn't feel the earth pulling on him. He wouldn't feel heavy in his own body. If he let go of an object, say a hammer, it would float beside him as though the two were standing still in space. For that man, in free fall, the hammer and his body would simply drift together. This realization sent Einstein's imagination into overdrive, because the situation is eerily similar to what an astronaut experiences floating in deep space, far from any planet or star. There, in the void, a spaceship at rest or moving at constant velocity experiences the same thing, weightlessness. Inside that spaceship, objects remain still relative to the astronaut, unless nudged, in which case they glide in a straight line at constant velocity. No heaviness, no invisible pulling, no sensation of being dragged down. Einstein realized something radical. Falling off a roof near Earth and floating in the middle of space aren't just similar, they're physically identical. The equivalence principle. This became the foundation of Einstein's equivalence principle. It says that for the person falling, their experience, what physics feels like inside their little reference frame, is indistinguishable from the astronaut in deep space. The falling man is not in fact accelerating from his own perspective. He is coasting smoothly along a path just like the astronaut. He is an inertial observer, someone who experiences no forces, no weight, no resistance. But wait a second. To us, watching from the ground, the man is absolutely accelerating. His speed is increasing by 9.8 meters per second every second. And when he hits the ground, that acceleration will be painfully obvious. So who's right? Einstein's insight was to say, both are right, but the falling man's perspective tells us something deeper. The only real acceleration happens when you're stopped by the ground, or when a rocket engine fires to push you off your natural path. Free fall itself isn't acceleration at all. It's just motion along the straightest possible path through space-time. And here's where everything people get wrong about gravity begins. Gravity is not a force pulling you down. It's the absence of force. You, sitting in your chair right now, are the one being accelerated, pushed upward by the floor. The man falling from the roof is the one in free motion. Rocket Man and the illusion of force. Imagine now that our astronaut, let's call him Rocket Man, is coasting peacefully through the void. His ship moves at constant velocity, no thrusters on, no external disturbances. From his point of view, he is at rest, drifting forever. Inside the cabin, everything floats. No experiment he can do will reveal otherwise. This is what physicists call an inertial reference frame, a frame where the laws of physics behave in their purest, simplest form. Now compare him with our unlucky man falling off the roof. Both are weightless, both feel no force tugging on their body, both can drop an object and see it float alongside them. By Einstein's equivalence principle, they are physically the same situation. But here's the catch. Rocket Man's ship might eventually come close to a massive planet. From the outside, a distant observer could track his path and notice something strange. Instead of flying straight, his ship's trajectory bends ever so slightly toward the planet. To the outside world, he looks like he's accelerating. His velocity changes direction, and over time, he's drawn closer and closer. But inside the ship, Rocket Man feels nothing. His instruments register no jolts, no invisible tug, no deviation from constant velocity. For him, it's as though nothing unusual is happening. His path feels perfectly straight. So who's right? The outside observer sees a curve. Rocket Man insists on a straight line. The answer lies in Einstein's revolutionary idea. Both are right, because what counts as straight depends on the shape of space-time itself.
Curved spacetime. In everyday life, we think of space as a flat stage. Draw a line on paper, and the shortest path between 2 points is a straight line. But what if the paper is bent into a sphere? Suddenly, the shortest path looks curved to us in 2 dimensions, even though on the surface of the sphere, it's still the straightest possible path. These shortest paths on curved surfaces are called geodesics. Planes flying across the Earth always follow them. A flight from New York to Tokyo, for example, doesn't trace a straight line on a flat map. Instead, it arcs across the Arctic. On a globe, though, that arc is the straightest path you can take. Einstein's leap was to say that gravity works the same way. Objects like Rocket Man's ship or the hammer falling beside the man on the roof are just following geodesics. They are moving along the straightest possible paths through space-time. The problem is that space-time itself is curved by the presence of mass. So from a distance, those paths look bent. To Rocket Man, he's on a straight line. To us, we see him spiraling toward the planet. Both descriptions are correct, because straight lines in curved space don't always look straight. The illusion of attraction. Here's an analogy that makes this clearer. Suppose you and a friend stand exactly 1,000 kilometers apart on the Earth's equator. Now, you both walk due north. At first, your paths are parallel. But as you move, you'll notice that you're slowly drifting toward each other. Eventually, you'll meet at the North Pole. Did some invisible force pull you together? No. You both walked straight ahead, never veering sideways. The only reason you collided is because the surface you walked on, the Earth, is curved. Gravity, Einstein argued, is the same kind of thing. You, me, Rocket Man, the hammer, the planets, we're all simply traveling in straight lines through space-time. But because space-time is curved near massive objects, those straight lines look like curves from the outside. To us, it looks like the Earth is pulling the hammer down, or pulling the moon around it. But there's no pull, no force, no field, just geometry. The weightlessness of the astronaut. This explains something that confuses people about astronauts. When you see the International Space Station orbiting Earth, the astronauts inside float around as though weightless. Many people assume it's because they're far enough from Earth that gravity is weak. But that's wrong. At the height of the ISS, gravity is still about 90% as strong as it is on the ground. So why do astronauts float? Because they're in continuous free fall. The ISS and everything inside it is following a geodesic around Earth. It's not being held up against the ground by a floor. It's simply falling forward so quickly that it keeps missing the Earth. The astronauts aren't experiencing a force pulling them in. They're experiencing no force at all. That's why they're weightless. The truth is, the only reason you and I feel heavy right now is not because gravity pulls us down, but because the floor pushes us up, preventing us from following our natural geodesic through space-time. The problem with the rubber sheet.
If you've ever seen a documentary or high school science video about gravity, chances are you've seen the classic demo. A big rubber sheet stretched out with a heavy ball placed in the middle. The ball sinks down, creating a dip in the sheet. Then, if you roll a smaller marble across the surface, it curves around the dip, orbiting the heavy ball. It's neat, it's memorable, and it's wrong, or at least dangerously misleading. Why? Because it tricks your brain into thinking the marble curves around because gravity pulls it down into the dip. But that's just smuggling Newton's idea back in. The whole point of Einstein's general relativity is that there is no gravitational force pulling things down. The marble curves because the surface itself is curved. The path it follows is straight on the surface, even though it looks bent to us peering from outside. So if you really want to understand Einstein, don't imagine a ball rolling into a hole. Instead, imagine an object moving smoothly through spacetime. Its path is a geodesic, the straightest possible route. What makes it appear curved is the geometry of spacetime. Matter tells spacetime how to curve, and spacetime tells matter how to move.
You are the one accelerating. Now, let's revisit something we brushed past earlier. You, sitting in your chair right now. Newton would say that you're at rest. You're not moving, so there's no acceleration. The only forces acting on you are gravity pulling down and the chair pushing up. They cancel perfectly, so you're stationary. Einstein says, nope. There is no gravitational force. What you're actually feeling, the heaviness pressing you into your chair, is not the earth pulling you down, but the chair pushing you up. That push is a real force. It's the same kind of force you'd feel if a rocket engine were firing underneath you, accelerating you upward. In fact, from Einstein's perspective, you are accelerating upward at 9.8 meters per second squared, because the floor beneath you is constantly preventing you from following your natural geodesic through spacetime. That might sound absurd. I'm not moving upward, you might object. But remember, motion is relative. Compared to everything else in your room, the floor, the walls, the lamp, you aren't moving. But all of those things are inside the same reference frame as you, and that reference frame is not inertial. Relative to someone who is in free fall, say the man dropping off the roof, you are accelerating upward. He would see the ground rushing to meet him, not him rushing down to the ground. Acceleration as deviation from a geodesic. So what does acceleration really mean in general relativity? It's not simply your velocity's changing. It's whether you're being forced off your geodesic. A hammer dropped from your hand follows its geodesic perfectly until the ground gets in the way. You, by contrast, are not on a geodesic right now. The ground beneath you applies a force to keep you from falling, and that force means you're deviating from the natural path through spacetime. Think of it this way. The hammer falling is the object with no force on it. You, standing still, are the one being constantly forced off course. It's a complete reversal of how most of us instinctively think about gravity. We say things fall because gravity pulls them down. Einstein says things fall because nothing is pulling them at all. They're simply moving freely along spacetime. You are the one being pushed by the ground. But if we're accelerating up, this raises a strange question. If you and I are accelerating upward, along with the whole surface of the Earth, shouldn't the Earth itself be expanding like a balloon? The answer is no, because in curved spacetime, you can accelerate without changing your spatial coordinates. Standing still on one place on Earth requires constant upward acceleration, just enough to balance out the curvature of spacetime created by Earth's mass. In other words, in flat, empty spacetime, acceleration means changing position. But in curved spacetime, acceleration can mean simply resisting the natural path you'd otherwise take. So the ground beneath your feet is constantly accelerating you, not by moving you upward in space, but by pushing you away from the geodesic your body wants to follow. That push is what you call weight.
Why everything falls the same? One of the oldest mysteries in physics is why all objects fall at the same rate. Drop a hammer and a feather, ignoring air resistance, and they both accelerate toward Earth at exactly 9.8 meters per second squared. Newton explained this with his formula for gravity. The force pulling on an object equals its mass times acceleration. The mass appears on both sides of the equation, so it cancels. That's neat, but it raises a deeper question. Why should they cancel? Newton's formula involves two very different kinds of mass. On the left is gravitational mass, how strongly an object responds to a gravitational field. On the right is inertial mass, how strongly an object resists acceleration. Why should those two, which seem conceptually unrelated, always be identical? For centuries, this was just an odd coincidence. Scientists tested it with increasing precision down to 1 part in 10 trillion and always got the same result. Gravitational mass and inertial mass are indistinguishable. But no one could say why. Einstein's relativity cut straight through the puzzle. In his view, there is no gravitational force. Objects in free fall aren't accelerating. They're simply following their natural geodesic through spacetime. That's why all objects fall the same way. Because falling is not a force acting differently on different masses. It's just free motion, the same for everything. The only time differences appears is when something interrupts that geodesic, like the ground beneath your feet. But the fall itself? It's universal, effortless, and force-free. So, here's the truth. Gravity isn't a force pulling you down. It's the shape of space-time guiding everything along its natural path. The hammer falling from your hand, the astronaut drifting in orbit, the planets looping around the sun, they're all just following geodesics, the straightest paths possible in a curved universe. The only reason you feel heavy is because the ground is pushing you, forcing you off your geodesic. That push is what you call weight. And that's what almost everyone gets wrong about gravity. Thanks for watching, and I'll see you in the next one.